Right. Thank you so much for, first of all, inviting me over and being able to present over here at JuliaCon. It's a really great inspiration for me. In fact, my first time ever at MIT was 4 years ago when I took part in Hack MIT hackathon. And at that time, I was building my first ever machine learning project. So it's good to be able to come 4 years later and talk about some of the work that I've been specifically trying to implement and bringing more support for Julia and WebAssembly. Today's talk will primarily focus on what exactly is WebAssembly for those folks who might not be aware. So just a basic primer to what WebAssembly is, what's the current ecosystem of Julia and the support for WebAssembly, and finally some of the key challenges that we face with the adoption of Julia for porting it over to WebAssembly, and how the future kind of looks like, because a lot of the work that has been done has kind of been shelved, and there's some good opportunity for us to kind of crack into this enigma of being able to have better support for Julia and WebAssembly. So just a quick introduction about myself. I'm Shivay. I'm a developer relations engineer at Millisearch. It's a Rust-based search engine. And I'm also a WASM ambassador. WASM is a WebAssembly runtime. And you can connect with me on Twitter if you wish to learn more about Julia, about WebAssembly. So that's some of the work that I've been doing of late. So just as a basic primer to WebAssembly itself, because of course some of you folks might be knowing about it, some of you might not be. So today I'll just kind of uncover some of the misconceptions about WebAssembly and what WebAssembly is, and then we'll look at the current ecosystem of Julia and how well supported it is for WebAssembly. Now, the first question that always comes to people's mind is, especially if you're not coming in from a background of WebAssembly, is that, hey, is it just a web technology, and how is it related to assembly language, right? So is it like a new Java? Is it going to be replacing JavaScript because it's a web standard? So we'll be looking at some of the historical perspective, like how WebAssembly kind of started. Now, WebAssembly, in its simplest definition, is essentially a low-level byte code system that is acting as a compilation target for a lot of different programming languages. So whether you take functional programming languages or even object-oriented programming languages, scripting-based languages, today there's support for being able to take your language toolchain, whether it's statistically typed or even dynamic typed languages, to be able to get compiled into this binary format that is super portable and runs at near native speed, because of the fact that it does not have any of the dependencies. It's just your source code that gets compiled into this binary, and it's super portable. That means it's supporting multiple system architectures. So right off the bat, like, one of the biggest advantages that you can get from using something like WebAssembly is the lack of dependency of your primary binary source code that might be just working on a particular system architecture. Whereas with WebAssembly, it runs across multiple system architectures. So that's one of the biggest benefits that we get. Now, as WebAssembly started back in 2017, it started originally as a way to be able to run C++ code, or let's say non-JavaScript based code on the web browser, because browsers typically only are supporting JavaScript. So if you want to run some non-native JavaScript code in the web browser, you needed a way to be able to actually do that, because only JavaScript is supported. So that's where we got rise of assembly.js, and that gave eventually rise to WebAssembly, which is then coined together as a term by folks at Mozilla and a few other companies. So if we kind of look at the success of WebAssembly in the browser, we see that when we are when we are basically able to use more stronger or more compile friendly languages, for example, like C or C++, which are a lot faster in comparison to JavaScript, we see a lot of great use cases. For example, you could do in-browser video editing, in-browser photo editing, and right now we are seeing it being used in Microsoft Flight Simulator, tools like Figma or Adobe Photoshop, which if you were trying to do these operations with JavaScript, you just would not have been able to do so efficiently. But we are able to now see that they are very efficient in the browser itself, because of being able to use the underlying C++ code that gets compiled into the WebAssembly binary, and then you can run that inside of your browser. And if we kind of look at how this kind of looks like, so this is like a basic explanation that we take either C++ code, Rust code. We will find, like, you will use the appropriate tooling, for example, mscripten, which is a tool chain that allows you to convert your C++ code into the WebAssembly binary. So by using the appropriate tool chain, you'll get your source code or whatever module that you've written in C++ to get converted into the WebAssembly binary, and then you can just run it as part of your JavaScript. So you can just import it into a JavaScript file, and you can just very easily run it as part of your web application. So this provides you the polyglot environment because you can run multiple languages. You get very small binary sizes that run very effectively in the browser. But of course, the biggest question then we saw was that there are so many different advantages that we are basically getting from being able to run all of this code in the browser. So we wanted to, like, of course, the basic question was that can we replicate this outside the browser as well? Because we saw the great advantages with respect to performance, with respect to the portability of WebAssembly. So we wanted to take that portability and then also serve it for non-web browser applications. So that included being able to run it on the different type of edge applications, edge architectures, being able to run it in the cloud. And that is where now we are seeing a lot of use case of WebAssembly outside the browser. In fact, today, as of like 2023, there are more applications of WebAssembly outside the browser, in the cloud native ecosystem, in the server side, for being able to run like serverless functions, which are actually faster than a lot of your traditional Lambdas or Google Cloud functions. Just because of the fact that the size of these WebAssembly binaries is so small that it takes a lot less amount of time for the cold start, which we typically see in these functions. And also, as I've already previously highlighted, the cross architecture compatibility that we get with these binaries. So this is kind of the evolution that if we see in general in computing, that we started off with servers, we went into virtual machines, we then of course moved into containers, and now we are going to be seeing a lot of WebAssembly as technology that could coexist with containers, just because of the fact that it provides so many performance benefits when we are looking at from a grand scale of how effectively we could run these applications on edge. Because one of the use cases that you might probably come across is that as we see a lot of the adoption of specific technologies like machine learning, which are generally very compute intensive, if you want to run them on, let's say, edge applications or edge devices, where one of the biggest issues that we have is the resource constraint, right? They are very resource constraint in terms of the compute power that you get on these devices. So you typically have to optimize your machine learning models a lot, and that is what we can actually get with the help of WebAssembly. If we are able to actually optimize our machine learning models to be able to run efficiently on device, on edge applications. And of course, why should we care about all of this? So if you are not aware of Docker, one of the co-founders of Docker, Solomon Hykes, mentioned that in case WebAssembly actually existed back in 2008, there would have been no need for technologies like Docker to actually exist. Now, of course, he kind of then reiterated that that didn't mean that WebAssembly would actually completely replace Docker as such, but both of them can work very easily and coexist together to be able to truly make a lot of functional, highly quick functional applications, because a lot of the things that you could run on WebAssembly are short functions that that generally require you to be able to run them very quickly, whereas technologies like Docker could take part in managing some of the larger, longer running processes. So where WebAssembly would be very efficient is short-term processes that require you to be able to run them very quickly as well. So that is the main idea behind the WebAssembly integration, and how now we are actually seeing it being integrated with technologies like Docker. So this is like one such example, right, where you take something like a Rust code and you would use cargo build, which will then compile it into the WASM file, and then you can very easily then support it across multiple system architectures. So this is just one slide that kind of demonstrates what I had showcased about the cross compatibility of different system architectures. So right off the bat, you get support for multiple system architectures for WASM. And now, of course, when I spoke about that, how do we bring the overall compatibility of being able to run WebAssembly outside the browsers that's on the server side? So that's where the entire concept of WASI, or the WebAssembly system interface, basically comes up. So just think of WASI as this API that basically allows you to interact with a lot of the different operating system level features, or network connections, or even your file resources, because WebAssembly itself cannot actually do anything. It's in a very highly secure sandboxed model. So if you want to do any kind of operation, you have to make external system calls that allow for your WebAssembly module to actually interact with your external environment. So WASI allows you to basically do that, be able to interact with network resources, files, and all of that. And this is like just an example of how WebAssembly and Docker kind of run. I just wanted to kind of put that together for information, but we can probably skip over that. And that kind of brings us to where we are today, right? So of course, today we are seeing a lot of use case of WebAssembly outside the browser. But of course, a lot of the things that we'll focus on, the integration of WebAssembly and Julia, have been traditionally focused on how you can actually run them on the browser. And that's where we'll kind of now look at the current ecosystem of Julia and how Julia kind of has interfaced with WebAssembly as a technology. So we have so far been able to see that there's a lot of great use cases for WebAssembly. It's highly portable. It can run your code very efficiently. It allows you to take your non-native JavaScript code, run it in the browser, run it outside the browser. So let's see that what kind of compatibility we have today with respect to Julia. Now, before doing that, it's also important to understand that how traditionally Julia is compiled, right? So, of course, a lot of you might be aware that Julia is an interpreted language. It primarily uses just-in-time compilation, and of course, the underlying architecture is C or C++ APIs that basically are the ones that are responsible for it. So whenever you take your Julia code, it will get compiled into the LLVM, which is of course like a compiler, and then it will be compiled into one of the executables that will be focused on just one specific system format or system architecture. So right out of that, like, you don't get support for being able to run the same Julia code on one system architecture across multiple architectures because of this entire way of how we compile Julia. So there are primarily two different ways so far that we have kind of explored in order to be able to run Julia code inside the browser. So the first one that was kind of kick-started off by Keno Fisher, was actually initiative that he did around 4 to 5 years back, was trying to actually run Julia inside of the web browser. And the way kind of that he approached was that he took the interpreter, the Julia interpreter, and compiled into the WebAssembly binary, and then tried to run that inside of the browser. So this is one of the approaches, but there were a lot of different issues at that time that he kind of faced, and that led him to kind of shelving off the project for quite some time. And actually it has not been updated for the past like 4 years since we have actually since we saw this. And of course, like, this was quite nice, because what you see on the screenshot is the REPL, or the Julia REPL, and being able to actually run your Julia code right in the web browser. And another implementation of this was also with Pluto. You might be aware Pluto is a very well-known interactive Julia environment that allows you to interact with Julia code. Being able to actually run or interfacing that same approach that Keno took, of taking the just-in-time, or of taking the Julia interpreter and compiling it into WebAssembly by using the LLVM approach and using fscriptin to be able to do so. So this is another example where we see how you can actually run WebAssembly in the browser. Now, one of the other approaches that is showcased, and this is actually one of the newer ones that we have seen in past one and a half years, is basically taking advantage of some of the popular popular packages in Julia that basically include the GPU compiler or the static compiler, which basically have a completely different approach in terms of being able to compile your Julia code into WebAssembly. So this is more of the static compilation that takes place. So in this case, what we are doing is that we are not focusing on the just-in-time compilation, but we are using ahead-of-time compilation, and in which you'll basically take your Julia source code, and then using the GPU compiler.jl package, you're essentially using the ahead of time compilation to take your Julia source code and then get your final WASM binary. So this is like one such example of a source code where we are using the GPU compiler to declare a WASM target specifically for your Julia. So this again does use LLVM, but you have the capability of defining multiple target types. So in this case, we are using a WASM target to get our Julia code to compile into the WebAssembly binary, and then you can, of course, then run it inside of the browser with the help of your JavaScript code. Works fairly well. I would recommend everyone to kind of take a look at this simulation. It's fairly well known. And you can actually see like performing fairly well, like Julia performs fairly well. But of course, there are certain caveats with this specific approach. There is no dynamic memory allocation that can take place. There is no garbage collection taking place, because those are some of the limitations that we'll kind of explore. So there are some limitations in terms of like, how this particular code was actually run. There are like a lot of limitations that had to be put in order to successfully actually run this particular source code. So by running these like two different approaches, so the two approaches that we took, we kind of looked at was we like the Kino-Fisher route was to take the just-in-time the interpreter, basically the Julia interpreter, and then compile it with the help of mscripton into the WebAssembly binary and LLVM. And the other head was the static compilation, where we used the ahead of time compilation using these specific Julia libraries. But there are some subtle differences, right? So of course, the biggest one was compiling the interpreter or the runtime in the case of Kino-Fisher's route, or of course using these statistical tools which allow you to do statistical compilation, right? But there are some major blockers that were encountered during these approaches that kind of led to the entire Julia community kind of just shelving off working on WebAssembly altogether. And those are primarily because of the fact that at the time when these experiments were being run, WebAssembly itself was just not that advanced. So we're talking about the timeline of 2019, 2020. At the time, there's lack of proper support for garbage collection, multi-threading, which are, of course, very important, because it's not as simple as taking your Julia code, compiling it into the WebAssembly binary with the help of mscripton. Julia has a lot of other components that can be very complex. Julia has a lot of different external libraries that cannot just be directly compiled into WebAssembly, right? So it's not just simply taking your Julia code and compiling it into the WebAssembly. So there is also one of the biggest issues that we still kind of face today is that there is the WebAssembly debugging, right? So debugging WebAssembly modules is still relatively hard today as we speak. And of course, when these experiments were being run, a lot of extra code was being generated that is increasing the overall size of these WebAssembly binaries. We are looking we're easily talking about WebAssembly binaries of 50 megabyte, 150 megabytes in size. And of course, as I mentioned, thread support is not there. Then dynamic linking was limited, which of course, is very important specifically. And if we talk about the stack, how stacks basically work in Julia and in WebAssembly, those are completely fundamentally different. And those are also some of the issues which hindered the approach of being able to just take your Julia code and compile it into WebAssembly. But if we also talk about how WebAssembly could be interfaced with WASI, which of course is important to be able to run your Julia code inside of WASI. So far our focus was just running Julia on the browser, which has been the core focus of the community till now. I think barely any contributions have been made, and that's what I have been trying to, or at least our peer group has been trying to also bring support for Julia on the WASI side. And one of the use cases, in case you're wondering why to actually do that, is that with the help of WASI, you could essentially run HTTP services and also run Jupyter notebooks directly as web services. So that could mean that you could take some of your Julia code, especially let's say if you're doing a lot of scientific computing, machine learning on the server side on edge devices. You could very easily run your such Julia code on the server side with the help of WASI, right? So those are some of the implementation issues that we found that kind of correlate for both WebAssembly and WASI. So does this like fundamental question then, give rise to the question that, hey, is support for WebAssembly just so bad that we should we should forget about it? There is this one video this last year that was launched around Julia language and our experience with Julia and WebAssembly. So a lot of the things that I kind of covered right now go a lot more into depth about issues with the just-in-time compilation, issues with the garbage collection, the threading, the stack-based approach, or the differences in the stack-based approach that we see in WebAssembly. So this particular video kind of covers a lot in it. So I'll recommend you to kind of watch, if you want to dive deeper into it. But so of course the fundamental question is that, hey, I mean, why am I just giving this talk altogether in if the support is so bad, right? But we have to keep in mind that a lot of these approaches that we spoke about were done during 2018, 2019, and since then the overall system for WebAssembly has grown quite tremendously. So if we talk about a lot of the different proposals for WASM, for WebAssembly, specifically with relation to garbage collection, multi-threading, or the threading in general, have improved quite considerably today. And today there are proper infrastructures in place where a lot of these proposals are now in a state where now they are being launched for production ready, they are getting production ready. Of course, that doesn't mean that WebAssembly is very efficient and is proficient enough to be production ready at this very moment. We still kind of lack observability tools. Debugging WebAssembly modules is still relatively hard today. So of course, if you're doing that for your Julia code, it will still be hard. But because of the fact that today we have been able to get experimental support for just-in-time compilation of support for just-in-time compilation in WebAssembly, that also means that we could take our Julia aspect, right? So if you talk about your entire infrastructure for Julia, so there is the two major parts. There's the just-in-time compilation and your interpreter, right? So those individually could be implemented or could be ported over in WebAssembly today. Of course, again, the experimentation around this remains very limited in nature, and I hope that with the help of this particular talk, we are able to get community effort to bring in some RFPs and revive this entire process of being able to at least try out and implement not just the standard approach that we have seen so far, whether it's with respect to being able to take the interpreter, compiling it into the WebAssembly binary with the help of Emscripten, but also now try to take the approach. And here is one such thesis by one of the undergrads at or I think it is actually the postgrad at MIT, one of the students who kind of made this thesis, and this was published just in January of this year, in 2023, so it's extremely fresh. I'll recommend everyone to look at it because it is probably the best source for understanding the current ecosystem of Julia and WebAssembly in 2023. So I'll highly recommend everyone to take a look at this particular thesis paper that was published just this year. And this is kind of the roadmap for what the future work kind of looks like. So if we take a look at the static compilation that I kind of described, that's complete today. Being able to create user-defined functions, that actually is complete. What we see right now is being able to build a proper WebAssembly executable of the Julia runtime. That also, of course, covers the interpreter. That is somewhere in progress. So that what we mean by in progress is that implementations do exist today, but they are not by any means production ready, right? And finally, of course, we would want to ideally build a just-in-time compiler executable for WASM. That is, of course, one of the future works. And if we are able to actually build that and have the actual Julia code run inside of your WebAssembly, right, that would, of course, interface very well and have added support for being able to run it on WASM. So the open question is that, if with the current implementation that we see for Python, so if you look at the Pyodide project and how we are able to use the CGI style compilation, because of course, in comparison to, let's say, a Rust code, which could directly just take the Rust binary and execute it in WebAssembly, Python, of course, takes a different approach. It takes the CGI approach. So similarly, if we are able to use the stdi in and the stdi out approach, we can have support for Julia in WASI. And that in turn, what would that allow us to do is, it will allow us to actually use Julia for different different type of proposals that are running today for WASM, including WASI-NN, which is basically a approach for being able to run neural networks in WASI and take your popular TensorFlow, Onyx, PyTorch models, cross-compile them, and have them effectively train them for edge applications. So you're essentially taking your machine learning models, optimizing them for being able to run on WebAssembly, and then be able to run them on different type of system architectures. So our end goal with this particular talk is that by bringing in support for Julia and for WASI, we will be also be able to take some very popular Julia-based packages, libraries for scientific computing, for machine learning, and then compile them into the WASI and be able to run them on different type of system architectures on edge devices. That would make building machine learning models capable of Julia and WebAssembly very efficient. So with that, I'll conclude. Like, this is some of the future work of WebAssembly that we'll look at. But yeah, with that, I'll conclude today's talk. If there are any questions, I'll be more than happy to take them up. But you can connect with me on Twitter. Thank you.
Thank you for the wonderful talk. We have time for maybe one or two questions. Anyone? Yeah? Okay.
Thank you very much for the overview. I have a good friend who is into Rust and was just writing me like, oh, WebAssembly, is this something also Julia can do? And it sounds still like we have to wait another 5 years or something from like what I hear between the lines until Julia can really kind of do this as well. Do you have an intuition about this? Like, is it really far in the future or is it somewhere nearer?
Yeah, so I think, I mean, probably if you would have asked me this question 2 years back, I would have said, yes, we are probably 5 or 10 years into the line of bringing mainstream support for WebAssembly. But given the fact that how quickly the Bytecode Alliance, which is basically the entire open source foundation behind WebAssembly and all the different proposals, how quickly we are coming up to speed, right? And kind of filling in those gaps where we found those initially during the time in 2019 when we first saw like implementation, right? So I think we are accelerating. It's just that we need more community-driven effort to be able to run these experiments. Right now, it's just like, a few folks who are running it on the browser. Again, not a lot of support for the just-in-time compilation. So bringing in that support, bringing in the RFPs to at least try it out. I think like, if you look at like how much time it might take, I think like probably we could have some decent amount of support in the next 2 to 3 years in terms of the timeline. Just because that now WebAssembly itself as a technology is a lot more mature in comparison to what it was in 2019.
Thank you. We'll do one more question. Yeah.
So if the Julia JIT compiler is not compiled to a WASM executable, but has anyone just taken LLVM and made it a WASM executable?
Yes. So one of these particular projects that I probably showcased, I'm not sure if it is there. Actually, I didn't cover it. But if you probably take a look at this particular thesis, it actually covers one example where someone takes the LLVM and actually compiles it into the WebAssembly binary. So the experimentation for that has been run. Let me quickly check if I'm able to probably bring that up. Do we have like time for just 1 minute? Okay. So what I recommend is take a look at this particular research paper, and there's a link for LLVM compilation to WebAssembly. So you can probably take a look at that. So that experimentation has been run. So, and it has been fairly successful. Just to answer your question.